Anyone kayak? Yeah? In Pennsylvania? West? Yacht? Castleman? Yacht? Middle? Upper?
I did the upper and middle.
Upper's quite tough, isn't it? Upper's Maryland, isn't it? Yeah. I used to do this, so we have some boats in our garage, but I have to say, well, I don't do this. Never have, but I've done the middle yuck, I guess, on a couple of occasions in a hard shell. So yeah. So this is kind of interesting stuff to see. So yeah. So yeah, interesting stuff to watch. I think it's quite skillful, like ballet, I suppose. Okay, so I guess that's one of the applications of fluid mechanics in everyday life. Quite amazing to see. But we talked last time about why, among all of the topics in fluid mechanics, open channel or free surface flows are interesting, and that is because it has this ability to be able to choose the mode in which it flows. It's got this extra degree of freedom. It can flow in any channel quite shallow but quite quickly, or it can flow more deeply and more slowly. And it turns out that that behavior is basically in those two binary modes. So we'll talk a little bit about that today. I think perhaps we'll close up what we've been talking about in terms of the Shesi equation and the Manning equation, because those are perhaps the most usual applications in fluids that we'll use. And so just to summarize those, I guess I will say also that SRTs are of course open. I think it's useful to do those. I always read them. I think it's most useful to read the narratives of what people liked and didn't like, what people found useful and didn't find useful. I think it's useful for me to know that if you're in class or not in class, you identify one way or the other. So I'm curious how these different modalities of delivering this class work or don't work. So I would encourage you to do that. So they're open. You know, of course, that they close sometime before the exams. They're not available to us until after all the grades are in and the exam grades are in. So we can't take out our angst on you retroactively. So that's the reason for that, obviously. And that's not really the use of them. The use of them, I think, is to give some feedback for perhaps not improving things for yourselves, but improving things for your people who come after you. So I think they're... I mean, we've done things in a variety of modalities. We've been in class, we've done things online with quizzes, and so I'm kind of curious, and some of those things we haven't done before. We've given extra credit for quizzes. I'm surprised, actually, that not everybody has availed themselves of that. They're big. If I look at the scores for the quizzes, columns and names, there's lots of white space in there, which I find curious. But anyway, so I guess I was going to mention that SRTs are open. Is this another one? I guess it just started up doing something else and moved on to something. So back to pause that. Back to what we're talking about in this class. So today we'll carry on talking about open channel flows. We'll talk a little bit about the things that we've done so far, just to summarize. And then we'll move on to a topic which is for gradually varying flows. And so just to summarize from last time, when we developed our behavior for uniform flows, by definition, the definition of a uniform flow is that the depth doesn't change as you go from upstream to downstream. And so we used this figure specifically to explain what was going on, and that is that if the flow is uniform, then the depth of the flow, by definition, upstream and downstream, is the same. If the depth of flow is upstream and downstream is the same, then the velocity of the flow at each of these points has to be the same as well. And so in terms of the slope of the bed, the hydraulic grade line, which is the surface of the water, and the energy grade line, which is the slope of the water plus the v squared over 2g term, they all have to be parallel to each other by definition. So this is parallel to this, which is parallel to this. And in that condition, the important considerations is that we can basically draw a box where if this is length 1 and this is S0, this is the slope by definition. And if we go directly above like this, then if we draw this is horizontal, and this is SF, and this is 1 also by length, then it means that this is the viscous loss, the energy that's being expended in the system. Just like we can write Bernoulli between upstream and downstream, this is really Bernoulli written between upstream and downstream. This is our term which would be our equivalent for the HL term. And actually, I suppose in some respects, this is kind of equivalent to the HP term. Actually, I never actually thought about it that way, but it is. So if you wrote Bernoulli for this behavior, it would be upstream, upstream. Of course, this term here is this height, right, basically, plus V1, whoops, V, why is it not working? Because I had my finger on it, right? Plus HP. My writing's not very good. I know why. It's from last night. Plus the pressure downstream, plus the velocity squared term downstream over 2g plus head losses, right? And so this is just a manifestation of this. This is the head loss, viscous loss. This is the energy in, or maybe it's the energy rate in. And so the energy in is provided, this is basically the equivalent of S0, and this is the equivalent of SF. So if this energy grade line was horizontal, which it can't be for the reasons we've said, then there'd be no viscous loss in the system. So by definition, for uniform flows, where in a mathematical sense the change in depth as you go downstream is 0, that's all this term means, this is just a fancy way of saying that, then as a consequence of that we get out of it the Chézy equation or the Manning equation, which I'll just zip up in a second and write down for us. And that allows us to calculate what the flow rates are within channels. And so I'll zip up. And so if we have a channel that has some cross-section, don't know how well I can draw this. I can certainly draw it fine on its side. And that channel has a slope 1 S0, and it has depth y. And this is my perspective drawing of this. This is area. This is wetted perimeter, which we've drawn here. Then we can always get the flow velocity in this as a function of this constant, which depends on, it's equal to 1 for SI. I think it's equal to 1.49 for feet per second versus meters per second. The Manning coefficient multiplied by hydraulic radius, I think to the 2/3, and multiplied by the slope of the bed to the half. And if you want to get the volumetric flow, you just multiply the average velocity by the cross-sectional area. So hydraulic radius is equal to area over perimeter, and slope is just in units of it's unitless, right? It's this length divided by 1, whatever that is. And so typically these are very small numbers, fractions, less than 0.1, less than 0.01, less than 1 in 100. And so we rationalized this last time when we looked at the comparison, if you like, between our graphs for Reynolds number, and in case of our Reynolds number defined as a velocity, the density of the fluid, the characteristic dimension was the hydraulic radius, just out of convention, and the viscosity. We said last time that we're almost always turbulent, and we never came back to looking at this diagram, but from this, the value of this, I guess 1 over Manning's number, which is this term here, or I guess it could be K over Manning's number, this term here, is kind of a friction factor, nothing more than that. And so this would be 1 over n equals a small number. I guess these are numbers. Yeah. I don't know. 1 over n is small. 1 over n is large. I think that's the way that these are drawn, right? Because for friction factors, they start off large and they go smaller and smaller, I think, right? Or it doesn't matter. But the point is that we never use this graph. We're always in this region here. We're always in the turbulent region, and we define behavior in terms of a Manning coefficient. That's what n is. It's a number which is a Manning coefficient, uppercase M. M-A-N-N-I-N-G coefficient, and that varies depending on the pipe, the channel material, whether it's weedy, whether it's soil, whether it's concrete, whether it's brass, we saw as one of them. And so you can imagine that if you want to get a large velocity in your channel, you want an efficient channel, you can do a number of things. So if you want velocity to be large, then what do you need to do? You either have 1 over the Manning coefficient is a big number. You have hydraulic radius, which is a large number, or you have a slope, which is large. You can do any of those things to increase flow. Those are the design things you could do to change it. So this means instead of using a rough material, you could line the channel with concrete forms to make it nice and smooth, and therefore make this number large. You could increase the slope of it, maybe, if that's within your constraints to be able to do that, and you could make it increase. Or you could change the hydraulic radius, which means that if hydraulic radius is equal to the area over the perimeter, then you could increase the area relative to the perimeter. In other words, make it a more efficient section. And so you can actually do calculations to figure out what the most efficient sections would be. And we could just illustrate this with a circular section. It turns out that the most efficient circular section is to basically fill the height. The height here would be equal to the radius of this. And we don't need to show that, but you can imagine that if you're just filling the bottom of this channel here, then the perimeter is relatively large, and the area that you fill is not very large. As you fill this progressively higher and higher, the area increases and the perimeter doesn't increase so much. And so you can imagine that to get the biggest ratio of area to perimeter, you look at the most favorable section that gives you that. And we didn't talk about that last time, but that was kind of a footnote on one of the figures we had, I thought, actually. It's just here. Maybe it's there, right here. And that is that you can imagine that to get the largest area to perimeter ratio, you choose shapes for the cross-section of the channel that fill that. The most efficient shape for a circular channel is to fill it all the way up, rather than partly. The most efficient one for a triangular channel is to have it look like this. You can imagine, that if it looked like this, then there's a lot of perimeter to very little area. And the converse of that would be if it was like this. If this was a triangle with this angle in here, then this area here is very small relative to this perimeter here. if you open up the triangle. And so you can imagine that you can get those different coefficients. So you can imagine that you can get the most efficient section to do that. And so we won't belabor that point, but those are the controls you have to be able to do something, to be able to maximize the channel width. So that's really where we are with the simplest of these cases. Always turbulent, and therefore always depends on only a single coefficient, because this line is flat. We never draw this diagram like this, but we do know what these numbers are based on typical materials. And these are the parameters that you control to be able to do something about it. So that's what we dealt with before. So now what we'd like to do, I guess actually I have something here. So this is the other thing. So the obvious application of this is something like, I guess topical now, California is in drought. It's an El Nino year, so it's about to get a dousing of water. I lived in California in the Bay Area in 1982-83, which is an El Nino year, and it was the year that I remember horizontal rain all through the spring, and it was the year they were actually digging out the ski lifts in the Sierras, because there's so much snow that when you get off the lift, they're too low. The gantries were too low to do that. And so California, interestingly enough, gets most of its water from the Colorado River, which by the way, when it flows into Baja California, the Gulf of California, I guess it's off this map, the neck that goes around through Mexico, western Mexico, there's basically no water that goes into that sea now. All of it gets taken to LA in some form through an aqueduct system. The aqueduct system is quite controversial, was at the time. Colorado water rights, water from the Colorado River, etc. And it all gets used in another state. And so it is a controversial issue, although perhaps it's in place. If ever you've watched the movie Chinatown, Chinatown, it occurs to me, is all about issues over water getting into the LA water district. It's an interesting movie to watch. So just reminded of that, thinking about this. And so the kinds of things that the California aqueduct system would do are really the equations that we've talked about in terms of the Chésy equation to be able to do that. But that's no longer for us. So our interest now is in being able to understand why, in some cases, we might have flow that occurs in a channel that is relatively straightforward to understand, that we've been looking at so far. And why is it possible to be able to run at two different elevations? And so here, this is a hydraulic jump. The idea here is that since there's no water that's accumulating, if you look at the cross-section here, from continuity, the velocity upstream has to be much higher than the velocity downstream because of the cross-section that it's flowing across. And so the question is, why is it able to self-organize itself into these two apparently stable configurations, upstream and downstream of a point, and how do we go about being able to explain that? And so to be able to do that, what we need to do is think about the idea of the different flow configurations that we might have within our system. And so what we've talked about so far are uniform flows, where the depth of flow doesn't change from upstream to downstream. And the two other variants, I guess, are gradually varying flows, where it slowly changes from one to the other, and rapidly varying flows where the change in depth is much more extreme as you go from one to the other. And so to understand that, then we have to return to this kind of geometry. And this geometry kind of allows us to think as to what's going on. And so the idea is that if the upstream depth and the downstream depths are different from each other, then by definition the velocities upstream and the velocities downstream also have to be different from each other. If the downstream depth is smaller, then this velocity has to be larger. If this velocity has to be larger, then this separation for the energy line, in other words, v squared, v downstream squared over 2g, has to be higher than this. And so now, instead of the energy grade line and the hydraulic grade line and the slope of the bed all being equivalent to each other, now they're potentially, certainly these two are different from each other, these two. And for the reasons we've just stated, presumably SF is not parallel to SW for sure, and there's no reason why it particularly should be parallel to S0. And so that's the condition that we'd like to try and understand. And more importantly, we'd like to understand whether this occurs as a slope between these, which we didn't really see last time, or whether it occurs something like a step, which we saw the opposite last time, where it went from shallow to deep as it went downstream, but presumably it can do either. And so what are the conditions that explain that behavior? So we're going to now look at non-uniform flows, and specifically we'll look at gradually varying flows. I won't dwell on that, that's just my scribbles. And so the one piece of information we now need to do this, surprisingly, is we need a wave velocity. So wave velocity for fluids flowing in channels is the equivalent of you listening to me. I feel sorry for you. But the rate at which my voice gets to you is by the acoustic velocity of speed of sound in air. And wave velocities in water are similar, but they fall into a variety of categories. They're different in open channel flow than they are in closed channel flow, which is in this room. This is a fluid mechanics problem. We're sitting in a fluid, happens to be a gas, and you're listening to me, and the rate at which my voice gets to you is actually given by the speed of sound, which is equal to the bulk modulus of the air divided by density square root. If you cast your minds back, we talked about this basically 14 weeks ago. It's this expression here. And so if you know the modulus of wood or steel, and you know its density, you can calculate what the speed of sound would be in a bar or in the rock or in a rock. And so also for air, since we know that for air the bulk modulus is about equal to the pressure of air. So we're at 100 kPa now. So the bulk modulus of air in this room is about 100 kPa. The stiffness. Stiffness is 1 over compressibility. It's units of pascals. Compressibility is 1 over pascals. This is the isentropic expansion coefficient, specific heat, the ratio of the specific heats. This number is about 1.4 for air, so we don't have to worry about it. But if we substitute this into here, and we know that the pressure is equal, from the ideal gas law, is equal to RT, or KRT, and we substitute that in for this, then we lose both of these, and we end up with the speed of sound in air is equal to the ideal gas constant, the temperature, and this coefficient, in other words. So, it doesn't matter. The bottom line is we can calculate what the speed of sound in air is if we know those coefficients. And it's no different from the speed of sound for the P wave in solid. And I think we talked about this at the time. So if you have an earthquake offshore, the speed at which the seismic signal arrives on land, the earthquake arrives in eastern Japan from being offshore, is controlled by this seismic velocity, acoustic velocity. And for rocks, it's of the order of a couple of kilometers to 5 kilometers a second. And so if you are 100 kilometers offshore and it's traveling at 2 kilometers a second, then does that mean you have 40 seconds before the shock arrives on shore? So you can measure it on offshore, ocean bottom seismometers. You send that signal electrically at the speed of sound. Onshore, you get 40 minutes warning to turn off the gas, get out of your building, and be safe. And so there's some benefits. And those things are put in place, actually, by the way, in Japan and also in California. Automatic shutoffs for gas. Speed of sound in air, you can do the same thing. Do the calculation. It's much slower. It's about 400 meters a second, something like 600 miles an hour. If you look at the celerity wave, and we could derive it, but I'm not going to derive it. The celerity wave is different from the acoustic wave. So in other words, if you shout to someone, if someone shouts for some reason here to someone else in the bottom of the sea, the rate at which that will travel to you is the speed of sound in water, which is about, well, depends on actually, we could calculate it, I guess, based on this. The stiffness of water is about 2 GPa. And so it's about the same as rock. And so the speed of sound in water, I think, it's about 1,000 or 1,500 meters a second. So slower than rock, but faster than air. But that's when we're talking about the wave speed for surface waves, then they're different. It's not the same as the compressional wave that arises by a sonar pulse, by doing a ping, for instance, and seeing what it bounces off, or shouting at someone if you're diving, if you can shout underwater. It's the speed of travel of a celerity wave. And we never derived it, and I don't think I'll derive it today, but the celerity wave speed is this. It's proportional to two things. It's proportional to what planet you're on. Gravity on this planet is 9.8 meters a second, and it's proportional to the depth of the water. And so in other words, in this case, this is the depth of the water. And this is the so-called shallow wave approximation. And it's the only one we'll use. And it turns out that if you could calculate it, it's a function of depth. So if you're 1,000 meters deep, you can calculate, so 1,000 meters water depth multiplied by 10 meters a second squared is 10 to the 4, square root of 10 to the 4. So cc is about square root 10 to the 4, which is about 100 meters a second. And so if you're in 1,000 meters of water, then you can calculate what that is. And so 100 meters a second is actually the speed that a tsunami will travel at. So quite fast, really fast actually. It's of the order of the speed of a plane. So much faster than you think. Of course, when you're way offshore, when it's quite deep, then the size of a tsunami is probably a few centimeters only. It's only when it runs up onto the shore that the depth gets constricted, then kind of the water piles up and it becomes a big event. But basically, offshore it's a very, very small amount. So we could do the derivation for that, but we won't. But we will make the final comment, and that is that this shallow wave approximation is going to be good enough for us. And it is that the speed of the wave is controlled by the depth of the water and g. And so this responds to the fact that relative to the wavelength of the wave offshore, and by the way, the wavelength of tsunamis offshore are perhaps a kilometer or many kilometers. So this wavelength is the distance between peaks. So for shallow wave, by definition, the depth of the water relative to the wavelength is small. So y is small relative to the wavelength. For deep waves, then the same deal. The wavelength, if it's the same wavelength here, as you'd expect, refers to this. So it's relative to the wavelength. So it's the wavelength of the wave relative to the depth of the water. And so it turns out that if you look at very deep waters, the deepest points on Earth are probably 8-9 kilometers deep, I think, Marianas Trench, maybe 12 kilometers deep, where the wavelengths are small compared to very deep depths. Then no longer does this hold, and the deep water full approximation is this. And you can show that in the middle of the ocean it conforms to this. This graph is just showing that in the middle of the ocean it conforms to this equation, and in a channel, which would be a shallow channel relative to the wavelength on the surface, like a river for instance, then we can get away with using this. Okay. So why on earth, when we're talking about channel flow, would we worry about the speed of a wave traveling in a system? Good question. So the idea is this. If you cast your mind back to when we talked about our three most important and favorite dimensionless parameters, we talked about Reynolds number, which is the ratio of inertial to viscous forces. We talked about Euler number, which is, just to remind you, change in pressure over rho v squared. Again, it's our jet engine at SFO pushing the truck into the water. And this is pressure, force, divided by inertial force, and Froude number, which is our inertial force divided by gravitational force. We haven't used this very much so far, but you remember by our definition of this, it was a velocity divided by square root gy. This square root gy is, of course, we now know the celerity wave speed. And so it turns out that the Froude number is a magnitude of a velocity, some velocity of flow maybe, relative to the wave speed in that fluid. And so the ramifications of this are that if you have a pond and you drop a pebble into it, then the velocity at which the wave train will go out from where you drop that pebble in is the celerity wave speed, if it's in a static medium. And so if you're looking down on it, what you'll see is if it was only a single wave, then if you take a picture at T1, T2, T3, T4, T5, there'll be all these concentric circles if you used a strobe, for instance, to do it. But if the water is flowing, then you'd get a slightly different picture, right? And so if you do the same thing with a strobe after you drop a pebble in at time t0, then if the water is flowing, then it would look like a whole series. These would be circles. They wouldn't be ellipses. They'd be a bunch of circles. So if I redraw that, here is where you drop it in. At time 0, you drop it in at this point here. In the time that it takes for this wave to develop around that circle, of course, the upstream part has flown an amount downstream. This part has flowed in an equal amount, and so it will just have translated. And so what you'll see would be a whole series of concentric circles that would be slightly shifted. And in this case, the flow velocity of this stream is less than the wave speed. If it was exactly equal to the wave speed, then this would be moving down exactly to this point in the time that it took for the wave to go out. And so what you'd see is if the flow velocity here was equal to the wave speed, square root gy, then it would look like a whole series of concentric circles that impinge on this point here at exactly a Froude number of 1. If you go above that velocity, then the picture that you'd get would be equal to this turned inside out. So you drop it in here, but this expanding circle would already have traveled downstream beyond the point where it could reach this. And so the relevance of this is if I'm talking to you and I'm sitting here, you can hear me. If I'm talking to you but I'm moving out of the room at the speed of the sound, you'll just not hear me. And of course, if I'm moving faster than the speed of sound away from you, you don't have a chance of ever hearing me because the noise I make will never ever reach you. And so the relevance of this is kind of the same. If the flow velocity downstream is faster than the celerity wave speed, then there's no way that a disturbance downstream can communicate its effect in any way to anything upstream. And so that's the relevance of the Froude number. And so this break between a Froude number of 1, where it is just communicating. If it's less than 1, then if you dip something in the water, it will communicate that information upstream to some point. If the Froude number of the flow is greater than 1, then it can never communicate any information from what's going downstream to upstream. And so that's relevant because when we're looking at these systems where we're looking at this behavior here, you could think of it in terms of that. So something here is going on downstream, something here is going upstream, and for some reason they don't really seem to be able to communicate. And it's because they can't communicate that it's happy to stay in this configuration downstream where it's deep and flowing slowly versus upstream and flowing fast. And so that's kind of the rationale of why we'd look at wave speeds, celerity wave speeds in water to be able to define that behavior. Okay, taking too long to do this. All right. So, bottom line, we'd like to be able to use to understand these behaviors. We know that we've said already that in terms of open channel flows, we think that all of our behavior is turbulent. So Reynolds number might not be a very good indexing parameter for us to understand what's happening in the system, because we know we're always going to be greater than whatever we said was a Reynolds number is greater than 500. We know we're always going to be there. And so it now becomes that the Froude number is an important parameter to use. And it's important in this way. If we have a flow, for instance, that we have the same volumetric flow going in each of these cases, it turns out that we can use the Froude number to be able to index the kind of flow we have. Whether we have what is referred to as a supercritical flow, which is above a critical velocity, in which case the Froude number is bigger than 1, in which case it can't communicate upstream, where there's a fast flow rate in a very shallow flow depth, or an equivalent volumetric flow, but gives a lower flow velocity and a relatively deeper depth. And so that's the understanding that we need to be able to use to be able to understand how flows may self-organize in this particular way. So that's our challenge. So to do that, we go back to Bernoulli, and we idealize our behavior not different from what we've looked at already, and that is this channel that has a slope of the base of 1 over S0. It has an upstream depth, a downstream depth. Because the downstream depth is shallower than the upstream depth and the same volumetric flow is occurring, the velocity V2 here has to be larger than V1 by definition, right? And if V2 is bigger than V1, then this length here has to be bigger than this length here. And so that defines the bed slope, defines part of our system. On top of this, we have the height of water between upstream and downstream that defines the hydraulic grade line. So this would be HGL on the top. And then the velocities that are predefined by a constant flow rate prescribe a lower velocity upstream than downstream because it's squeezing through a smaller gap. And so that gives the height of this energy grade line. This is EGL. And we're interested mainly in the slope of this. The slope we'll call SF. But as we said before, really, it's like Bernoulli's equation, it's just HL. If this number is 1, then this is a length which is HL. HL is basically equivalent to, HL is equal to SF times L, right? If this length is L, so the units of head loss are length, the units of slope are a length divided by a length, so they're dimensionless, but if you multiply a dimensionless number by a number with units of length, you end up with the right units. And likewise, I guess, if we want to, S0 multiplied by L would be kind of equal to HP, right? Pump head. It's not relevant, I guess, if you have an open channel, because you can't really have a pump to do it, but it's equivalent to that. Okay, I digress. So, with this defined as our system, we can write Bernoulli's equation. Pressure head, velocity head, elevation head upstream. Pressure head, velocity head, elevation head downstream. Head loss within our system. What we'd like to do then is be able to rearrange it in terms of certain components. I guess, all right, I lied. Let's, instead of do this, let's make this equal to Z1 minus Z2. Yeah, okay. Yeah, I guess it could be HP if we had it in there, but really we have gravity driving flow. So it's not HP. So what we're going to do is we're going to take these two values here for Z2, And we're going to note that we could replace them by this term here, which is the same as what we've written up here. What else? We're going to realize that if you look at the magnitude of this height here, relative to this is just the pressure at point 2 divided by the unit weight of water. Right? The pressure we get here would just be the height of water above us if we're sitting on the bottom of the channel. And so what we can do is we can substitute this as y1, I think, and we can substitute this as y2. So these are two terms here. And if we make those two substitutions, we end up with this expression here. We want to be able to define this head loss term. We've already said what it is. If HL is equal to SF times L, which is really just what we've written up here. Then if we make the substitutions for Z1 minus Z2, which we've already done here, and we make the substitution now for this, and gather terms, then this is the term that comes out of it. The difference between these two components. And so now we have Bernoulli's equation, which includes viscous losses, so it's kind of the energy equation, the one-dimensional energy equation. It's written in terms of depths of flows. It's written in terms of velocities, upstream, downstream, and upstream. And it's written in terms of the slope of the bed and the slope of the energy grade line in the system. If the slope of the energy grade line is 0 and the slope of the bed is 0, then we lose these terms and we're just left with the Bernoulli term. So why do we want to write it this way? Well, we want to write it this way because typically when we define a channel flow, we know what this is, right? This is perhaps a design parameter. We know what the slope between Parker Dam in Nevada to LA is on average over hundreds of kilometers. And so this is one of the design parameters that we'd have in our system to be able to do that. And so really all we're going to use is the Bernoulli equation. All right. So this is the equation that we have. Let's not worry about dropping any of the terms. So right now it includes Bernoulli. It includes the driving gradient, which is this, which is just Z1 minus Z2, modified in some way. And it includes the viscous losses, which is really the HL term. So that's what these two terms are. And the rest is just the pressure term. This is pressure. And this is V squared over 2G. Okay? So why are we doing this? Well, the other thing that we can do is we can take this same equation, unadulterated, and we could, for instance, rewrite it, I suppose. So we could rewrite this equation between the upstream portions. We could write as y1, which is this term. And we could take the velocity term here and we could write that as equal to the y2 term, taking this down here, plus v2 squared over 2g, plus the slope of the energy line minus the slope of the bottom surface, the bed of the river, multiplied by the length over which we measure it. And so what we've done is we've come up with two terms, and we'll call these specific energy. Specific energy upstream and specific energy downstream. That's what this term is here. And that's convenient for us because now what we can do is, since it includes terms which are part of the flow regime, so these are kind of abstract terms. This is a design parameter, slope of the bed. This is the energy grade line, which is kind of an abstract parameter which we can't really put a number on very easily. But these are two very physical quantities. It's going to be the depth of flow upstream and how quickly it's going. and the depth of flow downstream and how quickly it's going downstream. So what we could do is we could try linking them. And so if we try and link those, we take a channel which has some width b and some depth y and has some flow rate going on it. And what we define is a flow rate per unit width. And we'll call that lowercase q. So flow rate per unit width is, take a 1 meter wide portion of the channel and how much flow goes through that. You take the total flow, divide by b, and that's what gives you this, right? So total flow rate, this is going to be in meters cubed per second. This is in meters. And this is going to be meters squared per second. If we know that the total flow rate is going to be the velocity times the width times the depth, this term here is obviously just cross-sectional area, then the b's top and bottom cross out, and it's just given by the velocity times the depth. And so if we come back to our definition of specific energy as depth times the Bernoulli term, what we could do is we could just multiply this term by 1, which is this here. And if we multiply this by 1, then this term on the top is just equal to v times y all squared. And we've just said that v times y is equal to q, and so this is equal to q. And so now we have a specific energy term which is a function of the depth of flow, wherever we are, upstream or downstream, and it's a function of the flow rate per unit width, which is not going to change as you go from upstream to downstream, right? If you have a deep flow here and a shallow flow downstream, the flow rate per unit width, total flow in the channel is the same. As long as the channel doesn't get narrower by changing B, then the flow rate per unit width is always going to be the same. So this is going to be something that won't change as we go downstream. So now what can we do? This does have a purpose, by the way, so don't think we're going nowhere. You may think we're going nowhere. So this is our expression, defined as we wanted to. Flow rate per unit width, gravity, channel flow depth, channel flow depth. If we set this equal to 0, then we get an equation that looks like this. We set it to 0 by multiplying by y squared. So in other words, if we multiply this by y squared, this becomes y cubed, and this becomes y squared, and then this is the expression. We set it equal to 0. And the reason for doing that is now we have an expression that only has y squared, y cubed, doesn't have y to the 1, but it has y to the 0 in it, I guess. So this is clearly a cubic equation. We know that a cubic equation has 3 roots, and so if we plot energy versus y, the two terms of this equation, on some plot, then we'll get a plot that looks like this. We'll get some curve, and it will have 3 roots. And 3 roots mean that for any value of energy, for a specific value of energy, which is this dashed line here, there'll be 3 values. The 3 values will be this root here, this root here, this is a depth of, so this is depth, this is energy, this is a depth of 0, this is a depth of a positive depth, this is a negative depth. So this is a negative depth. Don't know what a negative depth is. It's an unreal number, and so we don't care about this. But we do care about these other roots, because what these roots represent are, they represent basically, if we drew, I can't draw it very well. Actually, let's draw this. If we drew, this is our reverse hydraulic jump. So this is the depth of flow upstream. This is the depth of flow downstream. It's backwards from our hydraulic jump, which was shallow upstream, deep downstream. And this physical height here, this depth of flow, is basically the height of flow that we have here. And these represent the two potential configurations that the flow can be in. It can be either flowing very slowly at a very deep configuration, or it can be flowing very quickly at a much shallower configuration. And each of these flows have the same energy associated with them. They're equivalent to each other. The energy losses are the same in each of them. And so that is basically the behavior that we have in terms of writing the Bernoulli equation that includes the energy terms, which is really the one-dimensional energy equation. We write it in a slightly different form to be able to get something which we call as specific energy. We note that the energy from the upstream and downstream should be the same, and so it gives us a rational way of being able to figure out exactly what the depths, two potential depths would be. Okay. So a bit complicated, but nonetheless. And so this explains the fact that we could get one flow, but we have two ambiguous depths to it. It could choose either one of them. The other points which I won't belabor is we can also find the coordinates of this. It turns out that at this point here, at the nose, the tip of this nose, this point here, the Froude number is exactly equal to 1, interesting enough. And so this is this idea of being able to communicate upstream. This is where the ripples in the channel are all concentric circles, but they're all concentric on this physical point. If I zip up here, it's this condition, where the flow downstream is exactly at the same velocity as the communicating celerity wave going upstream. And so the other two coordinates on here, which I'll just quote, are that the magnitude of the, so this is the critical depth, which by definition is just the depth at the nose, or the depth where the Froude number is equal to 1. This one here is the Froude number is less than 1. And this one here is the Froude number is greater than 1. So-called supercritical and subcritical. And we'll go through this in more detail next time. And the one parting shot that I have is that this length here, the minimum energy, E min, is equal to something like, I can never remember, 3yc, 3 over 2yc. So this is the critical depth. The depth of flow where the celerity wave velocity is exactly equal to the flow velocity. And the magnitude of minute energy at this particular point is equal to 3 over 2yc. And if you go down here, you can see how you do that. We just minimize this function. It's not particularly important, but it is important to know what the ordinates of this are. And so we don't really have any time to do anything useful with that today, but next time in our parting shot on Monday, where we'll finish this off, we'll talk about how we use that to be able to say something about flow configurations. So, interesting stuff. I think it's interesting stuff. All right.